Curing is the hydration process that occurs after the concrete has been placed. To gain strength and harden fully, concrete curing requires time. In around 4 weeks, typically over 90% of the final strength is reached, although strengthening may continue for decades. Hydration and hardening of concrete during the first 3 days is critical. Abnormally fast drying and shrinkage due to factors such as evaporation from wind during placement may lead to increased tensile stresses at a time when it has not yet gained sufficient strength, resulting in greater shrinkage cracking. The early strength of concrete can be increased if it is kept damp during the curing process. Minimizing stress prior to curing minimizes cracking. Properly curing concrete leads to increased strength and lower permeability and avoids cracking where the surface dries out prematurely. Traditional conditions for curing involve by spreading or pounding the concrete surface with water. Also, fresh concrete can be covered with wet burlap and/or plastic sheeting to prevent dehydration. Any interruption in pouring the concrete can cause the initially placed concrete to begin setting before the next batch is added on top. This creates a horizontal plane of weakness called a cold joint between two batches. Normally, in order to talk about the properties of a product, this product should be at least piece or component level. It's impossible to talk about the mechanical properties of a material if it's not in the if it doesn't have a form. Let's say that we produce a component out of concrete or reinforced concrete. Concrete has relatively high compressive strength but much lower tensile strength. For this reason, it's usually reinforced with materials that are strong in tension, often steel. The elasticity of concrete is relatively constant at low stress levels, but starts decreasing at high stress levels as matrix cracking develops. All concrete structures crack to some extent due to shrinkage and tension. Concrete that is subjected to too long duration forces is prone to creep. A common example of creep is the permanent sag in the shelf of an inexpensive bookshelf. When books are set on the wood shelf, it may sag slightly. If the books are removed after a short time, the shelf returns to a level position. However, if the books remain on the shelf for a long time, the sag increases, and when the books are removed, the shelf does not return to its original level position. The permanent sag is from creep. Tests can be performed to ensure that the properties of concrete correspond to specifications for the application. Different mixes of concrete ingredients produce different strengths. Concrete strength values are usually specified as the compressive strength of either a cylindrical or cubic specimen. For cube test, two types of specimens, either the cubes of 15 cm or 10 cm, depending upon the size of the aggregate, are used. This concrete is poured in the mold and tempered properly so as not to have any voids. After 24 hours, these molds are removed and test specimens are put in water for curing. These specimens are tested by compression testing machines after 7 or 28 days curing. Loads should be applied gradually till the specimens fail. Load at the failure divided by the area of the specimen gives the compressive strength of concrete. Concrete of given strength is identified by its class. A class 25-30 concrete has a characteristic cylinder crushing strength of 25 Newton millimeters square and cube strength of 30 Newton millimeters square, or 1 megapascal. We can say that 1 megapascal is 1 Newton millimeter square. Also, we can use dosage in order to define the concrete. Dosage is the amount of binder as weight in 1 cubic meter of concrete mixture. Uh, if we say that the dosage is high, it means that there is more cement to wrap the aggregate particles and bind them together. So this is a high quality cement or a high quality concrete. Concrete of given strength is defined by its class, we said. If we need a lightweight concrete with very low strength, we can choose 14 megapascal type. It's called this C14 concrete. Or if we are passing a very large span and we have very heavy loads, we need a high strength concrete. We can choose 80 megapascal, which is the C80. Extreme weather conditions like extreme heat or cold, windy condition and humidity variations can significantly alter the quality of concrete. In cold weather concreting, many precautions are observed. Low temperatures significantly slow the chemical reactions involved in hydration of cement, thus affecting the strength development. Preventing freezing is the most important precaution, as formation of ice crystals can cause damage to crystalline structure of the hydrated cement paste. If the surface of the concrete pour is insulated from the outside temperatures, the heat of hydration will prevent freezing. Concrete can be damaged by many processes, such as the expansion of corrosion products of the steel reinforcement bars, like this one, freezing of trapped water, fire or radiant heat, seawater effects, physical damage, chemical damage, which is called carbonation. It's a slow process that occurs in concrete where lime, calcium hydroxide in the cement reacts with the carbon dioxide from the air and forms calcium carbonate. The water in the pores of Portland cement concrete is normally alkaline, with a pH in the range of 12.5 to 13.5. This highly alkaline environment is one in which the steel rebar is passivated and is protected from corrosion. The carbon dioxide in the air reacts with the alkali in the cement and makes the pore water more acidic, thus lowering the pH. Carbon dioxide will start to carbonate the cement in the concrete from the moment the object is made. This carbonation process will start at the surface, then slowly move deeper and deeper into the concrete. The rate of the carbonation is dependent on the relative humidity of the concrete, a 50% relative humidity being optimal. If the object is cracked, the carbon dioxide in the air will be better able to penetrate into the concrete. Eventually, this may lead to corrosion of the rebar and structural damage or failure. Carbonation can be controlled by using low water cement ratio or by supplying low relative humidity, or it can be prevented by using barrier coatings to prevent ingress of water or carbon dioxide.